So let's just do that one real quick. So the problem you're referring to is this. Is it k to the negative 3.2 sine? Is it just sine of k? This? Yeah, this guy converges. And the easiest way to see it is to use the comparison test. So what do I mean by that? Well, what you need to understand is that you can rewrite this as 1 over k to the 3.2. And that resembles, this clearly resembles a p-series. Do you follow that? Yeah, so since this is less than this for k equals 1, 2, 3, etc., you get comparison. Does that make sense? Yeah, and again, if you guys have any questions about all those series, write them down or ask tomorrow. We can talk about them tomorrow. But we spent a heck of a lot of time on these, and me doing examples is not the answer. It's you struggling to learn them and then asking questions about them. Okay, so what's the big picture here? So let's consider an old friend. Now, recall from Calc 1, but you're not going to recall, but we did this in Calc 1. The tangent line to f of x equals e to the x at 0, 1 is 1, we'll write it as y equals 1 plus x. Now, again, you might not remember that, but this is a problem that most of you know how to solve. And one way to interpret this, at least sort of intuitively, and we're going to draw a picture in a second. Yeah, you can call it whatever you wanted. I called it y. Okay, so if we draw a picture real quick, or if you went to Desmos, but we're just going to sketch it real quick. Here's the point we're trying to make. The function f of x equals e to the x has a graph that looks like this. And then the line 1 plus x, its tangent looks like this. And so here's the idea, the intuition. The intuition says that e to the x is approximately 1 plus x when x is approximately 0. Now, we spent some time in Calc 1 trying to convey this message too. We drew pictures. We talked about this thing called linear approximation, which is a fancy word for tangent line. If you don't trust me, go plug small values in for x and see that this is true. Make a table of values, convince yourself. So what do I mean by that? If you're not following me, let me go pick up, give me a second. I will go to what is it? Oh my God. Losing my mind. Go to Google Chrome. I'll share that with you in a second. If I go to Desmos, what I mean that this approximation is or that you have this sort of approximation. If I do y equals e to the x, I get that. If I do y equals 1 plus x, I get this line just like I suggested. And so from a picture standpoint, the idea is that the red and blue are on top of each other near 0 when x is near 0. From a numeric standpoint, you can just compute some values to convince yourself. So do, for example, 0.2, 0.1, 0.01, etc., 0.001. So you take numbers close to 0, and when you plug them into that, to e, that you get that. And then if I do the same values here, you'll see that my approximations, look, I'm accurate to at least 1 decimal point at 0.2. I'm accurate to 1 decimal point at 0.1. Now I'm accurate to 2 decimal points, 3 decimal points, right? So the point is that when an x is close to 0, these things are in agreement. Okay, then, well, looking at this picture, one might ask, well, why can't we do better? Is there a way to get a better approximation? Because look, this is not a polynomial. This is the exponential function. This guy is a polynomial. And as you know, and as I know from teaching and from being a student myself, working with polynomials, whether we're adding and subtracting or whether we're doing calculus, is typically easier than working with trig functions or exponentials. And so this idea suggests, well, maybe there's a way we can approximate differentiable functions by polynomials. So what I mean in a more specific sense is the following. So we might be curious, and that is, can we do better? So I'll put better in quotations. Can we get a better approximation? You know, for example, perhaps a second, third, fourth degree polynomial. So think about it. What makes this approximation say not better? Well, this is a line. So what we're asking, is there perhaps a second degree which would have more curve, or a third degree that's a better approximation? And it turns out you can. So to see that we can do this, let's pretend it exists. So we'll start with the second case, the second degree polynomial. So let's call it, for a lack of a better word, let's call it P of x. Now, what does a second degree polynomial look like? A second degree polynomial looks like a number plus a number times x plus a number times x squared. So I don't know what A, B, and C are. I'm just putting them there. And the question I want to ask myself is, what would A, B, and C, what numbers should they be in order to be a better approximation? Now, it makes sense, based on what we know about this linear approximation, that A should be 1 and B should be 1. Now, why is that? You might say, I don't understand why you would say that, O'Grady. Well, think about it. What do we know? What do we know about a function and its derivatives? Well, I got this tangent line by saying, okay, I want to know what line has the same slope as my curve at a given point. And so we know the first derivative tells us that. And that's how I got this tangent line, because the derivative of e to the x is e to the x. And when I plug in 0, I get 1. So if my function p is going to be any good at matching this blue curve, it's got to be that its first derivative at 0 gives me 1. Now, the only way that's going to be the case is if a is 1, if b is 1. Well, technically, I guess a could be anything, but no, it can't, because it has to match at 0. So if p, let me rephrase it a little bit. If p is going to be a good approximation of e to the x, it's got to be that p of 0 is the same as f of 0, and it's got to be that the derivatives match. So since y equals 1 plus x is tangent at 0, 1, it seems that a equals 1 and b should equal 1. So it remains to determine C. That is, we have P of X is 1 plus X plus CX squared. Now, again, let me emphasize this. One of the big ideas that you were supposed to take from Calculus 1 is that the shape of a curve, its shape, how steep it is, whether it's concave up or concave down, you're supposed to take that, the properties of the first and second and third, those derivatives give us the shape of the graph. So since the derivatives of f tell us the shape of f, we'd expect P and F to match, so to speak. So what do I mean by that? I expect that f of 0 should equal p of 0. I expect that f prime of 0 should be the same thing as p prime of 0. And I expect, if I want a good approximation, that the second derivative at 0 should be the second derivative of p at 0. Now, don't forget, and maybe you forgot already, and that's a good, so don't forget that f of x is e to the x. F prime of x is e to the x. And f double prime of x is e to the x. And so that means f of 0 is 1, f prime of 0 is 1, and the second derivative at 0 is 1. So what I'm doing is I'm reminding you what the function is, what its derivatives, and what the values are at 0. So now let's look at the corresponding things for P. So what is P? Well, P of 0 is 1. What is P prime? Well, P prime, well, let's write it out explicitly first. P of x is 1 plus x plus cx squared. P prime would then be 1 plus 2cx. P double prime would be 2c. And then what is P of 0? P of 0 is 1. P prime of 0 is 1. And then P double prime of 0 is 2c. Any comments, questions, curiosities? Okay, so what does all this mean? Well, this is the values of P at 0, the values of P prime at 0, and the values of P double prime of 0. So we need them to match. So we need f of 0 to equal P of 0. We need f prime of 0 to equal P prime of 0. And we need f double prime at 0 to equal P prime at 0. But of course, this is the same exact thing. If we plug these in, this is the same as 1 equals 1. We already have that. Check. Then this is the same thing as 1 equals 1. Check. And then this is the same as 1 equals 2c. So what this tells us, for this to be true, this forces, if we want it to be a better approximation, this forces c to be 1/2. Now, look, I guessed that this should be 1 and this should be 1. But if you didn't guess, if you would have done A, B, and C, you would have seen these are forced to be 1. But I wanted to not kill so much time. So here's what the sort of the moral is. This, what we mean is the following. So this suggests that e to the x is approximately 1 plus x plus 1/2 x squared. Now let's go back to Desmos and let's add that picture. Instead of me doing 1 plus x, let's add that next term, which is 1/2 x squared. And if you look at it, there you go. I mean, the evidence is there. Not only is that blue curve right on top of the red, at least in here, but look at the numerical evidence. Look how accurate we are. So we didn't just guess at this, we reasoned it. We reasoned that a polynomial is a good approximation of any function if their derivatives match, at least at a specific point. Any comments, questions? Well, what do you mean if they don't match? Well, we're choosing them to match. So the question was, what if one doesn't match? Well, there's not going to be a case where one doesn't match. If we're reasoning what they need to be so they do match. Do you understand what I'm saying? So if I go back here, if I would have started here and instead of doing, if I would have replaced this with A and then B and C, and then I would have still gone through all this, I would have, the only logical answer would have been 1, 1, 1/2. Do you understand that? So it's not, if you do the reasoning correctly, you are actually determining what these constants need to be so that it matches.
So this means the first, when it's a function itself, that's for the first degree, right? And then the second one is for the B, and the third one is for the C. Or no?
I'm not quite sure what you're asking.
Since you said the last one, right, the double derivative.
You talking about this piece right here?
Yeah, so that's the value of C. So
that
does mean that the second one is the value of B.
That's correct. This has to be B, but I already guessed that these had to be 1. But again, if I wouldn't have guessed, okay. So look, I think your question is this: what if I didn't guess? Okay, don't guess. Just assume that this is A, and assume that this is B. So if I were not to guess, suppose I said, okay, A plus BX, right? What's the derivative here? Well, it's not 1, it's B, right? And then this is still 2C. All right, now plug 0 in. Well, here when you plug 0 in, you get A. Plug 0 in here, you get B, right? So then when I come down here, this would be A. We would get, this would be A has to be 1. This would mean B has to be 1, and then C still has to be 1/2. Does that make sense? So I could have done this way from the beginning, but.
But this is just for the 3, right? For the second degree.
That's correct, but there's nothing, but now we can do it for the 3rd degree. We could keep playing this game. There's nothing to stop us from playing this game. Why don't I do it again? I mean, we can repeat. So we can repeat this. So why not go again? So what do I mean by that? Let's call P now. We already know what the first few have to be. So what's the next one? We'll call it D. What should D be? Well, I'm not going to have to go through all the calculations again. All I need to know is what's this last term. Well, so we know that P prime, of course, is going to be 1 plus X plus 3dx squared. The second derivative would be 1 plus 6dx. And then the third derivative, which I'll use this notation, is just 6d. And then say that again. That's correct. And look, not only is it 1/6, there's a pattern hiding there. There's a pattern that's not just unique to E. This is going to be for everybody. It's a fascinating pattern. How did I get 6? Well, it's 3 times 2, right? And so right, that's exactly right. So since f, the third derivative of x is e to the x, we get the third derivative evaluated at 0 is 1. And of course, thus, we conclude, as you suggested, that D has to be 1/6, but I would ask you to think about this as 1/3 times 2, because there's a pattern there. Yeah. That's right, 3 factorial. So we can keep repeating this, and I would encourage you to try to do it, and you're going to mess it up at first, but you can keep doing it. So it turns out we could play this game forever. So we can keep going. And in fact, there's a pattern hiding out. So what is the pattern? Well, the pattern is yeah, I'll go back. Go ahead. If I go too fast, you guys got to tell me. I don't mind. Let me know when you're good, Emily. I'll take your silences. Yeah, okay. Gracias. De nada. All right. So here's the pattern, and this is what's quite fascinating. E to the x is going to be approximately, now we haven't really said what this means other than just look at the picture, but this is 1 plus x plus 1/2 x squared plus 1 over 6x cubed. And this thing goes on, and you could stop at any value you want of n. And the pattern is it's 1 over n factorial x to the power n. So there's a name we give to this guy, and it's based off one of the gentlemen who made this famous. This is called a Taylor approximation. And the polynomial P equals this creature this guy is called a Taylor polynomial. And there's a couple of really cool things that are fascinating about this. First off, and we're going to look at a picture in a second, but there was nothing special about us starting with e to the x. I could have chosen any. I could have chosen sine or cosine and played the same games, and I would have found the polynomial. And guess what? The damn pattern is very similar. It's crazy. So I'd like to go show a picture. I'm going to wait a few seconds because I'm sure people are copying. What I'll do is I'll go check the Twitter machine, see if what's happening, if there's a civil war yet or what's happening. Who's chatting? In the process. There's a Steeler game Sunday. That's all that matters, right? Oh my God. But the funny thing about all this stuff is the interesting thing about all this is literally they said that this was going to happen. Like that there was going to be all these mail-in votes because of the Roni, and they were going to take a couple days. And then I saw Trump tweet today that he should stop counting, and it made me think the only way he can win Arizona is if they keep counting, right? So he needs to win. He needs them to keep counting in Arizona, just probably not in Pennsylvania or Georgia, because that'll probably screw him. I don't know. What are you going to do? Okay, let's go look at some pictures because this is fascinating and it's much cooler than this election. let's add the next term. What's the next term? By the way, Desmos knows what factorial is. I suggested that to you. So let me add the next term. The next term is 1 divided by 6, x to the power 3. And now you'll see that that blue curve is almost completely covering the e to the x on when you move left to right. Now, it's not good. It's not good down here yet, but it's pretty good up here. Now, what's the next term? The next term is the fourth one. So let's look at the pattern. It's 1 divided by 4 factorial, and then it's x to the power 4. Now look what's happening. The more terms I add, the more this blue is taking over the red. Oh my God, it's like the election right now, right? I shouldn't joke about these things. Some of you might like the red side. I don't know. Or you're like, if you like the red, you say the blue's cheating. That's what's happening right now, right? But if it was the other way around, the blue would be saying the red's cheating, right? Oh, Lord, what a time to be alive. All right, let's add the next term. The next term is 1 divided by 5 factorial. And then this is x to the power 5. So this is, we could keep playing this game. And not only is the picture very indicated or very good at what's happening. Look, you can't even see red over here anymore. Now over here, it's not so good, but we do see it's getting better. This blue is creeping left now too. And if you look at these numbers are indistinguishable. And so think of this, not just as your Calc 2 homework. Think about how important this would have been 150, 200 years ago. Did you have a calculator 200 years ago? Did any human? How the hell would they know what e to the 0.4 is 100 years ago? Think about how hard that would have been. Here's a way that a human could, it would still be a pain, but a human could determine these values. You plug them into the Taylor polynomial. Let's see what these peeps are chapping about. They're both cheating. That's the old sports thing, right? If you ain't cheating, you ain't trying. That's what they say. And we know that in math class too. You guys all cheat. I always wonder, like, it's funny. I'd never ever cheated in school. I'm not lying. Never in my life. I never cheated. Ever. It's weird. I was like a personal point of pride. But I wonder, like, people who did cheat, when they get older, they look back. Like, if you're going to look back and say it didn't matter, right? So, like, why do it? Why be dishonest? It's not like if you cheat in Calc 2, your life's going to be any better than if you don't cheat. It's just not, right? It's just really not. I can guarantee you getting a phony B in here compared to a C or something is your life will be no different 5 years from now. So I always laugh when people cheated in these like lower. I just never understood cheating, but that's just me. Okay, so does anybody have a question about this? A comment? By the way, we could do this. We can get cute. Let me show you something. I could write this in a much cuter notion. I can put it in summation notation, and then some of you are gonna have heart failure when I do this. So if I put sum, let's say n goes from 0 to, let's say, 10. We'll go 10. And what's the pattern? Well, we know the pattern. It's what the hell was it? It was x to the power n, and then this is divided by n factorial. And so now if I go to the power 10, you could see that it's pretty much, the red is disappearing. What if I add it up to the 15-degree polynomial? Well, now I only have a little bit left. How about we go 20? Oh God, no more red, it's gone, right? The Crips have killed the Bloods, but then if you zoom out, not so fast, right? Not so fast. It looks like it, right? Well, we don't know. I mean, but what we do know is, look, we can now approximate this much further away from 0 than we could have before. So for example, if I look at the e to the 0, or let's say -4. Well, now if I plug it into this polynomial, that's pretty good approximation, right? Okay, this is fun. But yeah, you're right. So things are going, we got to keep working. But the first question you might ask yourself is, can I keep going? Can I go to degree 100, 1,000, 1,000,000? And that's sort of where we're heading. So if I go back here, this is where the series come into play. If we can foreshadow, why stop at n? What if I just left that ellipse there and said, let's do this forever? And so what we're going to do is we are going to graduate from the series of numbers that we've been studying. We are going to take those ideas and extend them to what happens about functions. So let me go show you something that we already have. Let's just go home. What do we have? We had a very nice formula before. We had this thing called the geometric series, did we not? And what did the geometric series look like? Well, we knew it was 1 plus x squared. Now, you might say we didn't have x, well, we had r, but let's just assume that instead of using r, let's use x cubed plus x to the 4th. And of course, we could do this forever. Now, let's just look at this. Okay, whatever. It is what it is, right? Now, look at, we know what this converges to. If I went the whole series, the series would converge to 1 divided by 1 minus r. Or in this particular case, 1 divided, whoa, get out of here. Our pets' heads are falling off. That's another extra credit we should give you guys. Dumb and Dumber, the original. That's a good movie. Now, what was the sum of this series? 1 divided by 1 minus the ratio. Now look at this. Don't look anywhere but between -1 and 1. Guess what? They're on top of each other. They're dancing right here. We don't care about down there. That's not between -1 and 1. Now, if I played the same game I did before, if I got cute, if I said sum, n goes from 0 to, let's say, I don't know, how about we do 23 for Michael Jordan? If I do the 23 terms, what is this? This is x to the n. And there you go. Look at it. Between -1 and 1, it's right on it. So this is a phenomenal idea we're seeing. We're starting to see that, oh my God, it looks like we can have the exponential function, or we can have this thing, which is some scary looking rational expression, but we can approximate it by a polynomial. It's pretty powerful. It turns out to be extremely useful. Just ask the physicists and the engineers. They live off of this. Anybody here take physics and ever study a pendulum? Have you guys done that at all? No, not yet. Simple harmonic motion. What the hell have you guys been doing with your lives? Pendulum, look. Ooh, hypnotized. All right. So we got lots of cool stuff to learn, keep learning. So let's get back to our, what time is it? 2:33. That's what the kids say. All right, so here's an awesome fact. There was nothing special about e to the x. So here is an amazing fact. We can do this for any differentiable function. So, and here's the pattern. I'm not going to do it again, but hopefully you trust that we did the example once, that the pattern is there, and you trust this is true. So we call P of x equal to f of 0 plus let me write it like this. Plus f prime of 0 times x plus 1/2 f double prime of 0 times x squared. And then this pattern is going to go up until we want to stop at any value of n. And so what's the general pattern? It's the same as before. It's the nth derivative evaluated at 0 over n factorial times x to the power n. So we call this the Taylor polynomial of f centered at 0. So this is overwhelming notation, but this is what we did last problem. We took the function and we evaluated it at 0. We took the derivative, evaluated at 0. We took the second derivative, evaluated at 0. Now, if we did this in general for an arbitrary function f, this is the pattern we get. Now, we can do this in general. There's nothing special about 0. We didn't always find tangent lines at 0. We could find a tangent line at any point, which means we can find a Taylor polynomial at any point. So this is going to look scary, but here we go. We can also define the Taylor polynomial centered at A. So that would be P of X. That would be F evaluated at A plus F prime evaluated at A. Now, here's the subtlety. It's times X minus A. Remember back in algebra class, you can shift a graph left and right by doing things? That's what I'm going to do. I'm going to shift it to A. And then this would be plus the second derivative evaluated at A divided by 2 times X minus A quantity squared. And then, of course, this pattern continues all the way up to the nth derivative over n factorial times X minus A to the nth. By the way, you could, I mean, if you have brave soul, you can write this in very compact notation. You can say the sum k goes from 0 to n. Use our summation notation of f to the kth power, or excuse me, the kth derivative evaluated at A over k factorial times X minus A to the power k. That's just a very scary and overwhelming formula. Well, this is all overwhelming for you guys. I get it. I remember learning this, like, oh my God. All right. So here's some cool Taylor polynomials, and maybe we will, well, let's just do one and then we'll show you what the other one is. So here we go. Let's change colors up. So the Taylor polynomial for f of x equals the sine of x at 0 is, here we go. Let's look at it. The polynomial is x. It becomes minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1/7, or excuse me, 1 over 7 factorial x to the 7th. And then this goes out. Now this actually is confusing for first timers, but it goes out. Look at the pattern here. All the powers are odd All the denominators are odd. There's no even. And if you remember anything about the function sine, you might have remembered in trig class, you learned that it's what's called an odd function because it has certain symmetry properties. And here you see it. Every power is odd. It's an odd function. And what's the last one? Well, you know the end. The last one has to be an odd number. So it's going to be -1 to some power. Just depends, right? And what's downstairs? Well, it's going to be, we could put a k here, and then we could put 2k plus 1 factorial over, or excuse me, times x to the 2k plus 1, because it has to be. Now, how do we rectify which is it going to be plus or minus? How do we figure that out? So what's the pattern here? So the first one's positive, the second one's negative. Then it's positive, then it's negative. So we know it needs to alternate. The question is, how do we know what this creature is? So let's see if this pattern matches. If k is 0, you get positive, right? And then it'd be, so if k is 0, this would be 1 over 1, and then this would be x, right? So it matches the first term. This would be the k equals 1 term. When k is 1, we get negative 1/3 x to the third. Perfect. When k is 2, what happens when k is 2? Well, when k is 2, you get 1 over 5 factorial, right? X to the 5th. So this matches, right? Now, why is this the case? Why? To see why, actually, before we see why, let's just graph it. That would be more powerful, I think. Let's graph it first. So let's first graph the sine. Now let's start graphing these polynomials. Y equals x, that's the tangent line, minus 1 over 3 factorial x cubed. See, that's pretty accurate in a wide margin. Then I can add the 5th term. And then the next term. And then the next term. Oops, a 1 here, that's important. And so you're seeing the same phenomenons happening. The purple, the polynomials, as I increase the degree, are taking over for the function. So a couple things to note here is that if I zoom out, though, I lose all the goodness, right? It's only good, right now, my approximation is only good between like -4 and 4. And so then you can understand there's all kinds of questions that we might ask, like, how do we, I've been writing these approximation symbols, but I'm not being precise about it. I'm being very sort of intuitive about it. How do we measure how accurate something is? How do we know when it's a good approximation? How do we know when it's not a good approximation? So this is a branch of math called numerical analysis, where people analyze these things. How high should my degree be of my polynomial to get sufficient accuracy? So these are important questions. Okay. So why is this the case? Well, let's just show you a couple reasons why. Well, note f prime of x is the cosine. The second derivative is negative the sine. The third derivative is negative sine. That derivative is negative cosine. And so the fourth derivative of sine gets back to where it starts. It gets back to the original function, which is just sine. So it alternates. It alternates between cosine, negative cosine, sine. And it's going to repeat. And so here's what we get. And on the next page, remember, we're going to be plugging the number 0 into these things, right? So we're going to be plugging 0. And what's the cosine of 0? 1. What's sine of 0? 0. So that means these guys are either 0, 1, or negative 1. Does that make sense? So we get a beautiful pattern. We can write that down. And since Halloween was the other way, we say a beautiful pattern. So what is the pattern? You get f of 0 is 0. F of 1 is 1. Excuse me, f prime of 1. F double prime, excuse me, f prime of 0 is 1. Ugh, losing my mind. Then you get 0. Then you get negative 1. And so what you end up getting is 0, 1, 0, negative 1, etc. And you could write it all down if you wanted. This is the fourth derivative at 0, etc. And so you see all the even, look at all the even derivatives. Even derivatives are 0. So that's why you don't see any even terms in the polynomial. And then the other ones are just 1, so that's why you get the following pattern. Thus, f to the kth derivative of f evaluated at 0 has 2 options, or 3 options technically. So it can either be it's 0 if k is even, and then it's negative 1 raised to a power. Well, what's the power? Well, I guess, let me be a little more careful. It's either, let's put it this way, it's plus or minus 1 if k is even, excuse me, odd. All right, so if we understand that that's how this is going down, and so what we end up getting is we get that the polynomial is x minus 1 over 3 factorial x cubed plus 1/5, 1 over 5 factorial x to the 5th. You know. And of course, we can take this as far out as we want. So we'll say the nth derivative evaluated at, so we know what that is. So how do we encompass that pattern? Well, we know the denominator is going to be n factorial, and we know this is x to the power n. The question is, what is this? This is going to be negative 1 to some power. So what power should we put on here so that it works? Well, don't forget, these aren't just n's. These have to be all odd numbers. So we have to, the way you represent a generic odd number is you say something like 2n plus 1. And you say something like 2n plus 1. And so the way to get the pattern to work is put a negative 1 there, or a power n there. And the way you think about this is, and this is for any positive integer n. Whew. So one of the skills that you should be able to have is that you should be able to determine these polynomials. The good news is, though, is we can use these polynomials to approximate other functions, though. So what are some uses of this? And by the way, does anybody have a question? So I guess we'll sort of end it, or not end it, but let's think of it like this. So the big question will be the following: can we extend this by sending n to infinity? And let me be more specific what I mean by that. So for example, do we expect e to the x equals 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed, etc., forever? Do we expect that the sine of x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th? Do we expect that we can somehow do this? Do we expect this to be true for each x? And so that's kind of the next question we want to answer. Our limited work today suggests that this might work. The reason is, as we saw, as we kept increasing the degree of our polynomial, the original functions, its graph was being covered up by the polynomial, the Taylor polynomial. So part of, if we think about that, we might say, okay, then why can't we, theoretically never end, and that would be a series? Can we extend those ideas? And it turns out to be, as you would imagine, tricky. You can't just, say this. And if you can, how do you say it, and when does it work, and when does it not? And so that's going to require us to do some new ideas. But if this is the case, then this is really, really useful, because it's telling us that we can essentially replace things with polynomials. And as you understand, adding and subtracting, multiplying, dividing polynomials, differentiating them, integrating them is usually a lot easier than dealing with complicated expressions. So in many ways, another way to think about this is this idea is almost asking, given any differentiable thing, any nice smooth curve, basically every smooth curve is just a polynomial in disguise, sort of. So, and that actually has lots of useful implications. All right, so this is a good place to stop. We will get into those ideas tomorrow. If you have any homework questions, I'd be happy to answer them. If you have any questions now, I'd be happy. Does anybody have a question or a comment? Going once, going twice. All right, then I will talk to you all tomorrow, hopefully, if someone has something they want to say. It always, oh, peace out. All right, homies, peace out. My kid told me I'm not supposed to say homie in public. I guess that must be school. Peace, homies. Take care, guys. Be safe. Thank you.